And so today we'll present some results of work that we've been doing in the past several months to investigate hydraulic fracturing, and in particular its closure in lab scale tests. And this work was done collaboratively with Jie, who was a research scientist at OU and now is an assistant professor at the South Dakota School of Mines. And just to give you an idea of what the presentation will evolve into, we'll start with some background information and motivation. Look at some hydraulic fracturing experiments we've done with AE, and look at the determination of the applied minimum stress in the block tests, and briefly discuss the cooling effect, and then summarize our key findings. So for those who maybe have forgotten or maybe are not much involved in this process, the Shmin obviously is critical to many aspects of reservoir development, and it is often determined using a minifrac or a micro-frac test. And the process involves interpretation of the pressure transients post shut-in or during reinjection to ascertain ISIP, reopening pressure, and closure pressure, the latter being the most commonly parameter used to represent the minimum in-situ stress. And to give you a brief history of the developments in this area, and it's important to review that most of the interpretation techniques for closure pressure determination are rooted in the work of Nolte, that he developed using a constant Carter-Leacoff model and a fracture that has a constant stiffness or compliance. And of course, that was pursued by Castillo, which applied that technique to actually determine the closure pressure, and subsequent contributions by Burry and Mukherjee, who extended the Castillo's work. And you will see here a few equations. The pressure change on the left is related to the G time through the Leacoff coefficient, square root of time since pumping, fracture radius, and the compressibility of the fracture. So if that red expression remains constant, then you get a linear trend when you plot pressure versus G time, and departure from that should indicate fracture closure. There are many different techniques to extract the closure pressure nowadays, and a lot of that is rooted in the fact that there are non-ideal behaviors that are observed from field tests. The normal behavior being just a normal constant Carter-Leacoff response with constant compliance, as shown on the left. And of course, there are situations where there are natural fractures present, so the concept of pressure-dependent Leacoff has been introduced, fracture tip extension, all of these to account for unexpected pressure transients responses. So Burry has done extensive work and developed what he called the holistic method. And the idea is to draw a tangent to the peak of the pressure versus G time, or derivative of the pressure versus G times G, and then use that as the closure pressure, essentially. And there are variations of that theme, again, depending on the particulars of the test result. This has been called by others since Burry the tangent method. And so there's also an investigation that kind of considered the possibility of the fracture compliance not being constant. And that goes back to the study of Ron et al. In 2001. They proposed a change in the stiffness as a point where the closure can be determined, and they wrote the expression for pressure change with time, not G time, but just time, and related that to the stiffness and volume change, essentially leak off and the fracture stiffness. And they pointed out that the fracture compliance or stiffness, as they call it, is not constant, and it changes, and that the process is complex. And they focus mostly on flowback analysis and try to use this change to extract minimum in-situ stress. As shown here in this plot, you can see that with post shut-in, the pressure declines on a linear trend, and then the slope changes here when the fracture starts to close, and they suggested that full closure occurs at some other time. And subsequent to that, in 2016, McClure and colleagues, they recast the equation in terms of G time, and developed what is called now a compliance technique. And they take the minimum of dPdG as the point of closure. And so we have now some kind of a, we have had in the recent past, some kind of a controversy in terms of what is the best way to detect closure. Is it the tangent method? Is it the compliance method? And the situation is a little bit muddied because field data tends to support the compliance technique, but at the same time, oftentimes, as is shown in figure 14 here, from a recent paper from the Canadian studies, hydraulic fracturing studies, that a large portion of the minifrac test did not have a compliance signature. Or they were weak in response. And so, you know, that's a source of still continued discussion. You know, we also heard recently, not too long ago, about the sunset solution, which tends to capture fracture closure, and it determines or studies, investigates, and ascertains that process, looking at only leak off as the controlling predominant mechanism during closure. And so that was our motivation then to do some lab scale studies to see if we can shed some light on the fracture closure mechanisms, and also look at the applicability of these different techniques for closure stress, closure pressure determination. And we have a polyaxial system at OU, and we can fit blocks up to 17, 18 inches into this. For these tests, we used 13-inch blocks, and different test configurations are shown here. And so we have utilized both. Usually the wellbore is drilled down to halfway, a notch is introduced, and the interval is filled with impermeable epoxy material to isolate the zone for hydraulic fracturing. And so for our testing program that we are presenting today, we chose 4 different blocks, 2 of them being granite, Sierra white granite, and 1 Sierra white granite was tested with oil, and 1 was tested with water, and was subjected to higher temperature subsequent to fracturing. We also tested a crab orchard sandstone and a Scioto sandstone. So these 2 represent intermediate and very low permeability rocks, respectively. And just to show you a sample of the workflow and the results that we obtained, we are showing the Sierra white granite here with oil injection. And our target was to control fracture propagation and prevent it from extending rapidly to the edge of the block. And so we monitored acoustic emissions and used that to help prevent excessive growth. At the same time, we had pump control set in a way that if pressure declined more than a particular rate, that we would shut in. And so you can see here we had 3 cycles of fracturing, and that's usually the normal workflow. We have the initial cycle where we initiate the fracture and extend somewhat, and then we use these 2 more cycles to try to extend it further. And at times it does get to the edge, as shown in this particular experiment, but does not have significant impact on the results and interpretation of the data. And this is just a movie to demonstrate the entire process. Maybe I'll speed it up a little bit. What we see in these experiments is that fracture initiation, as has been suggested and demonstrated in different lab experiments in the past, begins way before breakdown. And for this particular test, the fracture initiated at about roughly 1790 psi, and there were a few. We can ascertain that by a few AE events that we observed at that pressure. And then, of course, the pressure continues to increase to about 3,500 or so, where we have breakdown and we get much more level of acoustic emissions. And of course, we shut in, and then we go to subsequent cycles and repeat that. So this is cycle 2, and I won't play the movie, just say a few words about what we observed. In cycle 2, of course, we have the fracture reopening stage, and you'll note here that on the lower figure on the right, that the AE event count is plotted here, and you can see that during reopening, we did not see a whole lot of, very few or no acoustic emission events. It may be that there were very low amplitude that we could not detect, but at any rate, during the propagation phase, we do see an increased level of acoustic emissions, and then subsequent to that, when we get to fracture extension or the second quote-unquote breakdown, then we have a larger increase in AE level. So yeah, as I said, we repeat that, and we have 24 sensors that are recording the acoustic emissions, and we call a recorded piece of hit as an event if it's detected by nine stations. And so this is for stage 3, again, very similar in terms of its response, not much AE during reopening pressure. But if you map the AE and then try to superimpose that on the fracture geometry that we perceive, then we see that initially we had at least in cycle 1, we had a nice, reasonably penny-shaped circular fracture that, of course, became asymmetric with subsequent cycles, and in cycle 3 tended to propagate more in the northwest direction for our block. But then you see that there's a very good agreement between the AE cloud and the fracture geometry, and this is the retrieved hydraulic fracture actually. And you can see here, probably there is an outline here of that initial fracture, which is fairly penny-shaped, and we can see the asperity height that we obtained using a laser profiler, and so higher ground here and kind of more flat or smoother surfaces there. And what is interesting is that obviously there is fracture surface heterogeneity, which then obviously impacts the closure process. Also, it is interesting to note that the acoustic emission cloud is mostly distributed where the fracture surface has lower asperity and so flatter. And so where the fluid goes, it seems the acoustic emissions occur. So these are higher stress zones, and so the pressure was not sufficient to propagate the fracture there, and so it attained the figure that you're showing. So that was just one of the experiments, and so now we move to the actual work of determining the actual applied. So we know what SHMIN we have applied, and we're trying to see what the lab tests tell us. And we use different techniques for this, for different block tests that we have done. So this is for the oil injection into the Sierra White granite. And we use the reopening pressure, and reopening pressure gives us 1266 psi. The ISIP is about 1332. So compared to the 1250, those are very good. And I should emphasize here that our DFIT cycles begin after the third cycle of fracturing. So, the first DFIT cycle, is the first cycle after the third fracture propagation cycle. And so we can see right here that the closure pressure obtained from the so-called tangent method is very low, about 732, and compared to 1250. The compliance technique provides a higher estimate, a better estimate, still a bit lower, 1124 PSIs. And fracture reopening in the Sierra White granite with oil injection is fairly representative of the closure pressure in the crab orchard also. In the crab orchard, we also use oil, so the reopening pressure is 1521 compared to the actual applied stress of 1500 PSI. And for the Sierra White granite fractured with water and Scioto sandstone, which is a very permeable sandstone, the reopening pressure is very low, so suggesting that the water penetrated the fracture because of the high permeability of the rock itself and the fracture, and so underestimated the fracture reopening. Now, for the Sierra White granite oil injection, ISIP of 1332 on the high side, and as we expect. And for crab orchard, also 1531, a little higher than the applied stress. So, ISIP gives us an upper bound. And we can see that in the Sierra White granite subjected to water injection and the Scioto sandstone both. So it's consistently higher, but it's fairly objective in terms of estimating the applied stress. Now, the closure pressure from tangent method from the Sierra White granite subjected to oil, as I mentioned, it was 732 PSI. For the case of crab orchard subjected to oil injection, it turned out to be 911, both underestimations. And for the Sierra White granite subjected to water and Scioto with water frac, also we see that the tangent method provided a lower estimate, but the compliance method actually provides a good estimate of 1286. That's for the Scioto. Tangent method provides a value of 1286 in this case, which is good. So there's a contrast between the predictions of the tangent method for the permeable Scioto sandstone and the low permeability rocks. For the low permeability rocks, it tends to underestimate the closure pressure. For the permeable rocks, its prediction is reasonable. Now, going to the compliance method, in this case, we are looking at the Sierra White granite with oil injection. We see a clear signature, as has been suggested by McClure and colleagues, taking the minimum, and that is about 1124. For the crab orchard sandstone, we cannot detect a minimum, so it's very difficult to apply the compliance to that. There might be ways to look into the data further to try to process it and see what actual value we can extract from it. We didn't do it. We just said, okay, here is the suggested technique, and so we're just going to see if we can see a signature to take the minimum or the closure pressure out of it. And then here we are looking at the results for the Sierra White granite with water injection. Again, the compliance method provides a higher estimate than the tangent, but still kind of low. And for the Scioto sandstone, with water injection, high permeability, in this case, we don't see a signature in the compliance approach. So there's also a finding that we have, and that is that if we do multiple cycles of injection fall off, that tends to make the compliance signature disappear. So the signature is dependent on the injection history, and I think that's why it is suggested that the first cycle be used for that. And so that suggests that there is, there's that influence of or the competition between leak off and fracture stiffness change is impacted by the multiple cycles of injection. So and this is for the Sierra White granite. We see the same thing occurring here, that we do have a signature for cycles 1 and 2, but in cycle 4, we don't see any signature. Cycle 3 is not shown. That was a very short cycle, so its impact was not significant at all. But we see this consistently throughout all of the tests. So, so what, one of the interesting questions that still remains is that what is the process of fracture closure? We had these discussions, I believe, when the sunset solution was presented in one of the webinars. And so if you go back to the plot that Ron had presented, we can see there's a point that the fracture starts to close, and then the response of the pressure subsequent to that is determined by the competition between the leak off and the fracture stiffness. And so our system is stiffness as a whole, in this case, say the fracture. And so if the leak off is variable and stiffness is variable, obviously you're going to get different profiles for the pressure history. And then obviously the fracture, we can ascertain from this, and they did not really say this explicitly or did not discuss it in great deal. We can see that closure is a process, that it starts and then it ends. And of course, we are referring here to mechanical closure. So at the end, there's mechanical closure taking place, although the fracture is still hydraulically open and can take fluid. So, our experiments do shed some light on the actual closure process, and so we will see that this has some bearing on the technique to extract closure pressure using the compliance technique. So if we divide the process of fracture closure into 3 phases, we have phase 1. So we can call that pre-closure. Phase 2, which is actually the transient or progressive closure of the fracture, and again determined by the net product of leak-off behavior and the system stiffness compliance. And of course, then we have a linear response at the 3rd stage, then where the stiffness is constant, compliance is constant, and so we can call that post-closure. And so we, as we've seen before, usually the idea is to take the minimum here as the pressure that represents the closure pressure. And so to just kind of summarize the compliance approach, in our experiments, we have seen that sometimes in some tests we have a very strong compliance signature. Sometimes the signature is okay, it's adequate, and at times we do not see one. So that poses a challenge in terms of, well, how can we apply the technique with confidence? And so let's skip that one. So what we are suggesting, based on, again, on the data, is that we can take the first change in slope as the signature for closure. That first change is the first indication of change in compliance, and so that should be taken as the closure pressure. The reason we could say is that if we go back here, that the phase 1 very likely is a hinge closure stage, a short-lived maybe hinge closure stage, and then that stage, that is the change in slope from phase 1 to phase 2 represents transition from hinge to zipper. That is, the tip starts to close at that stage, and we should take that to be the minimum. The closure pressure representing the minimum in-situ stress. And so if we take that idea and try to apply it to the data that we have, we can see that for the Sierra White granite with oil injection, we get a closure pressure of 1283. And for the Crab Orchard sandstone, we get a closure pressure of 1505. And so you can compare those with 1250 and 1500. So a little on the higher side, but the difference is very small. And the estimates are very good. And you can see that here for the Sierra White granite with water, 1292 versus 1250 applied stress. And for the Scioto sandstone, 1229 versus 1250. And of course, recall that if you try to apply the conventional compliance technique, we would not be able to find that minimum. So, you know, this provides a workaround for the high permeability cases. So again, you know, if you recall, for the Scioto sandstone, the leak off essentially dominates the closure pressure. So we can't see a compliance change signature, and so this technique can circumvent that issue. Now, cooling effect, and we have a lot of data that we haven't processed yet, but I will show you what we have, and so I'm going a little bit faster than I expected, which is fine. We'll leave more room for discussions. And so what we did in some of these tests is that we heated the block subsequent to fracturing and our DFIT cycles. And the reason we did that, it's not because, you know, we couldn't heat it initially. We just weren't focused on the breakdown pressure. We feel that, you know, the decrease of breakdown pressure with cooling is well understood and well established, so we didn't want to do much there. And so we decided to just do our hydraulic fracturing first, and then heat it up, and then do a few injection cycles and see what the impact is on, say, ISIP reopening and closure pressures. And so the polyaxial frame can be heated to 300 degrees C. You know, in the experiments that we have, we didn't go to that high. Again, you know, we try to keep it below 100, and that's just, you know, for to warm up essentially to higher temperatures. So the working with high temperature vessels, you know, is kind of risky, and so you know, you have to kind of grow into it, and so that's what we've been doing. And so we plan to do higher temperature tests soon, but the results are very revealing nevertheless. So we monitor the wellbore temperature during these tests, and the temperature of the block on the surface, not shown here. We also obviously monitor the pressure and all that for different times and cycles. And sharing with you here the results for the Sierra White granite, we realized, and you would expect this to be the case, that if we don't increase our injection rate, that the cooling level is insignificant, particularly for this case of low permeability Sierra White granite. So we increased our injection rates to be able to see a higher level of cooling. So then, you know, from 5 milliliters to 15 milliliters per minute. And on the upper curve, you see the flow rate and the pressure, and you do see that, you know, despite the fact that we're increasing the flow rate, that there's a trend of reduction in the pressure, the maximum pressure that we have. That rollover pressure keeps going down, and you can also see on the lower figure that the block temperature is fairly constant and on the surface, and then the wellbore temperature is declining, continued injection. What's interesting also is that the wellbore temperature recovers rather fast post shutting. So, and we did not obviously, because we said that with multiple cycles, that compliance signature becomes difficult to detect. So, you know, we didn't see anything there. So what we did instead was to use the so-called tangent method, you know, ISIP reopening pressure, and since then we have also taken the first departure from linearity as an indicator too, not shown in this particular table. And then, so we also recorded or calculated the cumulative heat loss during multiple injections, and determined also the flow impedance. And so clearly, you can see the trend here that the reopening ISIP tangent method, the peak pressure, there's a rollover pressure, all of those decrease with cooling. Flow impedance obviously decreases, as you would expect, as the fracture opening tends to increase. And so the reopening pressure, the trend, you can see it as a power law reduction of the reopening pressure with cumulative heat loss. And so it's reminiscent of the poroelastic stress, except that the sign has changed. So the back stress would tend to increase your closure pressure. Here, cooling tends to decrease that. And we can see that with the peak pressure observed. Same thing with the ISIP and closure pressure. And in this case, we see the same trend. This is from the tangent method, closure pressure from tangent method. And so what did we have here? This was reopening pressure and the peak pressure side. Yeah. So closure pressure and ISIP also follow the same trend as the other two, as you would expect, again, because the cooling is in a way reducing the stress that the fracture is feeling, and so the fracture would have to come into contact at a lower value of pressure. So the key points that you would like to emphasize based on our work to date. High quality AE monitoring can assist in controlling hydraulic fracture initiation and propagation. So it may be stating the obvious, but implementation is not easy. So we've been able to do that, and with fairly high level of success. And the majority of AE takes place subsequent to breakdown, or in this case, if you have multiple cycles reopening, and then of course after shut-in, we have a lot of activity as well, suggesting that there is some propagation right after shut. And an important finding that I did not emphasize during the presentation is that our net pressure was relatively high, so about 300 psi, and it was a bit lower in some, but higher in others. But this is a good representation of all the tests that we have done, and so that's an interest, I would guess, because generally we think that it's really low, but at least for the fractures that we have at this scale, we see that they're high. And on the physics of closure, our results suggest that there will be different stages of fracture closure, phase one representing possibly a hinge closure, and transitioning to a zipper style closure, and then ending with mechanical closure, and still having a hydraulic pathway within the crack. And so what that suggests, two things I think that are of consequence. One is that perhaps we can take the first signature as shown here as the onset of mechanical closure, and so that should be representing the closure pressure. The other thing is that this entire process, from the onset of closure to the end of mechanical closure, does not depend only on leak off. So solutions that would rely on that assumption perhaps need to be revisited. Clearly, the process of now a joint or a natural fracture closure needs to be considered. Now, for rocks that are of high permeability, such as the pseudo sandstone, the leak off dominates very likely, and so the assumption that everything is determined by the leak off coefficient is probably okay. And what else do we want to say? And ISIP, and we are aware that of course ISIP has drawbacks when you use it for interpretation of field scale tests, but there are also corrections that can be made. And so in general, though, it does provide a fairly reliable upper bound on the closure pressure. What is interesting is that the first signature using the compliance technique comes close to the value of ISIP. That it overcomes that tendency to still have a lower estimate when you use the compliance technique. And another piece of information that is worthwhile is that we re-examined some of the minifrac tests or micro-frac tests that were done in Kismet. For those of you who are not familiar, this is a project that was carried out in the Sanford mine. It's a predecessor to the essentially collab. So pre-collab activity. I mean, these are different projects, obviously, but same location. And this is test 9, and you can see here that the ISIP, when we applied that to the data, provided 21.16 MPa for the Shmin. And if we take our realization of the closure pressure based on the compliance technique, we get roughly 21 MPa, which is very close. And another thing that was of interest was that the reopening pressure for this particular test and other tests at Kismet was very low. So and the only way we can make sense of that is that there are natural fractures present, and so some of those were taking fluid earlier, and then they were not propagating anymore, so the system was pressurized subsequently until the hydraulic fracture opened. And again, that can have bearing on other hydraulic fracturing tests that might be done in fractured rock. For geothermal applications, etc. And I should also mention that we like to express our appreciation to Tom Doe for providing the data for that. And then, as we mentioned earlier, cooling clearly impacts the opening and closure if you have multiple injection flowback cycles. And if not, if it's a very short injection period, likely the impact is not significant, but multiple injection cycles for sure, there will be an impact on the interpretation of minimum in-situ stress. So that's all the technical stuff that I had to present, and I would like to thank you and wish everyone a happy fall equinox, which is coming up the 23rd of September, this Saturday. Of course, depending where you are, and it can come earlier. So, thank you much.
Thank you, Ahmad. And you do have some questions, and I'll just walk through them. Syed Farouk Ali is interested in, what do you mean by ideal and non-ideal leak-off? Arguing that leak-off is steadily occurring as the fracture propagates.
Right. So the ideal would be right here. So you will see that we have this expression remaining constant because leak-off is constant. It does not change, and it invades the porous rock based on the Carter leak-off model. Now, when we say non-ideal means you have features present in the rock, such as natural fractures, that tend to open with increased pressure. So then now you don't have porous media diffusion. Now you have leak-off into natural fractures, or you have tip extension, or height growth, height recession, things that do not fit in the initial assumption of the nullity where we did the analysis.
Thank you.
Great. And Ali Danashi, Ali's question is, what do you consider the relationship between S3 and the fracture closure pressure to be?
Well, yeah. So if I understand that correctly, and maybe he can just expand on that a little bit. So is S3, that is what we have applied, is what the fracture feeling? Is that what the question is?
Ahmad, I'll ask the question myself.
Okay.
When you say fracture closure, do you mean by that that the fracture is closed?
No, well, so what we said was that the way we interpret that now is that when we go from hinge to the onset of zip closure. So that's when we would like to suggest a closure begins, and so the pressure is closure pressure, or min. So what we're suggesting is that this is a transient process that takes time for complete closure. So we don't want to take the pressure here to be the closure pressure. If you take it at the minimums, that still gives you a lower value. So it's right here when it first starts to close at the tip, it seems.
So this is something that you have arbitrarily defined and used in your analysis.
Well, no, what I'm trying to do is try to see which of these points best represents what I know I have applied, right? So I know I have applied a particular stress to the fracture. And so then what I see is that, okay, well, this point gives me a better representation. And so then I also go to my theoretical construction of the whole process being a function of the fracture compliance and leak off, and then ascertain that, well, okay, this portion is, again, as others have done, that this portion is impacted by leak off and fracture compliance, and those are not constant. And so that changes with time. So we have essentially we have to make a choice. And so the choice is, where in this process is the fracture closing? Or when we say close, and in fact, it may be not relevant if the fracture is closed or not. What is relevant is that, what is the pressure at different stages of this closure, this closure process? Does it represent which particular point represents the SH min, essentially?
You see, when you shut in the injection, when you stop injecting, during injection, the fluid pressure inside the fracture is not constant, it's changing.
Yes.
And when you stop injecting, the fluid is still moving inside the fracture.
Right.
And the fluid is moving inside the fracture and occupies a larger portion of the fracture. The average pressure in the fracture is increasing,
Okay.
but the wellbore pressure is decreasing.
Decreasing.
And so you need to relate what you are discussing to what is actually happening inside the fracture. Anyway, thank you for your answer.
Sure. No, but I think we are kind of covering what you said. That is, so we're not taking the first point, obviously. So we are allowing for that, phase one to develop and transition to phase two. And so again, this is ongoing work, and so we will have to do additional analysis of this phase one, the character of this phase one, and see what it represents. But clearly, that this is a transition point. And so, and that transition point to us represents a change in the way the fracture is closing. And maybe that phase one is actually what you just described. So, but we need additional work to iron out some of these kind of wrinkles in the process. But thank you. That's a very nice point and good question.
And the next comment was from Professor Solomon, who was indicating that he's advertising next week's 2 weeks presentation, and they'll talk about a different method for measuring closure. Mohammed, would you like to say anything?
Sure. Let me just make a comment first on the previous question. The reopening pressure that you measured looks to be closer to the end of the mechanical closure that you defined than the start. So that becomes an issue. because reopening pressure should be closer to the minimum in situ stress. So there's something we have to resolve here.
Right. So see, the reopening, obviously, as you know, is impacted by frictional losses. Is and the fluid may invade the fracture way before it is open. So we have that hydraulic aperture that is not going to go away at the end of mechanical closure. So when we go back, that hydraulic aperture is open, available to some extent for the fluid to get into, and so that will impact the pressure.
Right. Exactly.
Yeah.
I totally agree with that. And that causes that the pressure that will open the fracture, pushing them apart, is the minimum in situ stress. I would think so. There is an issue here, but anyway, going back to my original comment that I made, I'm advertising next time meeting. We are going to present one of my graduate students, PhD students, who presented the technique that we developed in-house here. And we wrote a couple of papers on it, but we analyzed data, field data, and experimental data. And I would love to analyze your data too, where we found out that compliance technique many times does not work, or I should not say many times. Sometimes it works, sometimes it doesn't. Tangent technique, same way, but without sounding arrogant or anything, our technique works all the time.
No, that's great. And so, what our intent was not to, and if you notice, we avoided getting into the mechanics of interpretation in detail. And the reason is our intention was to explore the physics of the process to the extent that we can using lab scale. And then obviously the data can be interpreted in many different ways. Now, I've also, others have, told me that, well, if we give them, this data on the Sierra sandstone, they can still use the compliance technique to extract the data, and that's fine. But what we were trying to say is that if you just take the techniques as presented, they don't work all the time, as you suggested. And so, yeah, I'm looking forward to seeing, your proposed approach.
We'll send you something about, I know where you are, so
yes,
I will contact
we'll
you.
We'll be happy to share the data with you and see, if you can treat it and
sure. And we'll share the results with you. It's both ways.
Very nice.
Great.
Very nice. So Ed Sieberts is asking this $64 million question. Is whether or not you can translate these lab scale data to closure pressure at a field scale, or whether there are attributes of the field scale that complicate things even further.
So yes, that's a great question, Eddie. And so I think if we set aside for a moment the near wellbore issues, right, and then what is interesting is that we actually do see some of the features that are observed in the field, and I did not have time to show all of those.
Ahmad,
but I didn't show
Ahmad,
them,
my question was more related to the near wellbore effects at the labs.
Right. Yeah. So if near wellbore issues are there, yeah. So I mean that's always a problem. So we have here a test that we did that in fact created a very complicated fracture with large near wellbore tortuosity that we could not extract any useful information from it using any of these techniques, to tell you the truth. But yeah, so we do see some of those complications at lab scale. But overall, what we are saying is that if you have a very nicely executed field test, and you want to see which technique provides you a more objective estimate of the closure pressure, that these lab scales can shed light on that. That's so obviously we're trying to compare things in a perfect world, and so operational issues and the fact that you get complexity in situ. Yeah, those are all things that make the interpretation of lab results very challenging. And John can attest to that. I mean, some of the minifrac tests that have been done, at Forge, you see features that we don't see anything like that in these granites that we have because they are intact. So, but point well taken, yes. But in terms of, again, just going back to the concept of fracture closure and trying to perhaps frame that in a more clear way, I think lab scale data is very useful because you can control things a bit more.
Very good. Dmitry Potapenko has a couple of questions, and he enjoyed your presentation. I don't know whether you can read this, Ahmad, but the first question was, were you able to define or confirm fracture closure pressure in your experiment from the piston's position? Presumably something related to fluid displacement, I guess.
Yeah, maybe the flat jacks, possibly. I suspect.
Could be the flat jacks.
Yeah. So we in some tests we did not have that recorded. In some we do, but we haven't looked at it. We do see a response, and we do see a change in response, but we haven't analyzed it quantitatively.
Yeah. And then Dimitri's second question was, and actually it relates to this slide and to slide 33. What fracture-specific information do you think can be extracted from the analysis of the pressure behavior during phase 2?
Yeah, so I think we can probably get leak-off information for some of the tests for sure, and then as you suggested, there possibly we can try to extract some stiffness data. I don't know if you had said that or not, but the fracture compliance, that is the natural fracture compliance, maybe we can extract that from these. But we haven't done those. These are ongoing kind of questions and work that we expect to continue for the next hopefully year or so. And if we get additional information that we have extracted from the data, we'll be happy to present it again in a different seminar.
Well, I think that sort of wraps up the questions. And you've had a number of comments congratulating you on the work, including one from Steve. I share that. I mean, you guys, this is fantastic work. And I think the nice thing, as you said, is that you're not advocating. You're taking a multi-partisan position and trying to look at the physics of closure, which I think is really great.
Thank you very much. Thank you, John.
Yeah, thanks everyone.
Thank you.
And tune in 2 weeks to hear another interpretation of closure pressure.
See you all. Take care. Bye-bye.